All right, in this section, we'll talk about section 1.2, dealing with representing functions. And we're going to be talking about things like using formulas. We'll talk about some of the various types of formulas that are taught in calculus. Also, we'll look at how to graph a function, also finding a slope. We'll do a little bit of review of some of the things that we talked about in college algebra. Also, we'll talk about graphing a piecewise function and talk about power functions. And also, we'll talk about how to graph functions of higher degree 2. And then we'll talk about how to use tables and do transformations of functions and graphs. So that's basically what we'll look at in this section and in this video. So here we're going to consider 4 different approaches to defining and representing functions, which are formulas, graphs, tables, and words. Okay, so we'll start out by using formulas here. That's the first topic. The following is a brief catalog of families of functions that are studied systematically throughout this book, and they are all defined by formulas. And in this case here, we have polynomials, which are of the form f of x equals to a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on, all the way down to a sub 1 x plus a sub 0. The coefficients are a sub 0, a1, all the way down to a sub n. Those are real numbers where a sub n is not equal to 0. And the non-negative integer n is going to be the degree of the polynomial, which is the highest exponent in that polynomial function. All right. The nth degree polynomial can have as many n real zeros or roots, which are values of x, where f of x does equal to 0. And if you were to graph it, it does correspond to points at which the graph of f intersects the x-axis. Second kind is a rational function. Okay. Now, rational functions have the form f of x equal to p of x over q of x. P and q are polynomials. Okay. Now, the domain of a rational function is going to be the set of all real numbers, with the exception of where your denominator equals 0. Because as we know, division by 0 is undefined. And then you have your algebraic functions, and those are constructed using the operations of addition, subtraction, multiplication, and division. Also, that's constructed along with roots. Here's some examples, like f of x equal to the square root of 2x cubed plus 4. And also f of x equal to x to the 1/4 times x cubed plus 2. And then you have what they call exponential functions. They have the form f of x equal to b raised to the x, where the base, which is your b, is not equal to 1. Okay, and it is a positive real number other than 1. Now, this one is closely associated with the logarithmic functions. Okay, those two are closely associated. Now, logarithmic functions are the form f of x equal to log to the base b of x. B is greater than 0 and not equal to 1. So again, b is a positive constant other than 1. Now, the exponential function has the domain consisting of all real numbers, whereas logarithmic functions are defined for positive real numbers. Right. And then next you have what they call the trigonometric functions. Now, trigonometric functions are these 6: sine, cosine, tangent, cotangent, secant, and cosecant. Now, what's also important are their relatives called the inverse trig functions. Later on, when we get into the next chapter, we'll talk more into those 6 trig functions. Also, there will be another video that I will be doing that talks about those trig functions. I'll go heavily into trigonometry for those who are not familiar with that particular subject. And then the 6 trigonometric, exponential, and logarithmic functions are a few examples of a large family called transcendental functions. Okay, so if you look on the next page, you're going to see that illustration of what transcendental functions. Usually you have your trigonometric functions, exponential functions, and logarithmic functions, but there are many more transcendental functions. But in this course, we're just going to focus on these 3. And the one on the left, you'll see your polynomials fall under rational functions, and also rational functions are algebraic functions as well. So polynomial and rational functions are algebraic functions. Okay. All right, next we'll look at using graphs. And in this case, formulas may be the most compact way to represent functions, but graphs often provide the most illuminating representations. Okay, so here are a couple of examples where you have graphs here, like the snapshot of a traveling wave packet. That is what its graph looks like. And also the probability of getting at least one pair of 6s after n number of throws of 2 dice. And this is defined for positive integers n. Okay, so those are just some illustrations of what graphs, how we can use graphs to pretty much answer various questions or problems or explain various situations. Now there are, excuse me, there are 2 approaches to graphing functions. One of them is by using a graphing calculator and also using software. Those are powerful and easy to use. Now, such technology easily produces graphs of most functions encountered in this book. So we will assume that you know how to use a graphing utility. All right, and also graphing utilities, however, are not infallible. So here we're going to strive to master what they call analytical methods, which are paper and pencil methods to analyze functions and make accurate graphs by hand. Okay. Now, what's important is that both technology and analytical methods are essential and must be used together in an integrated way to produce accurate graphs. All right. And now for linear functions. One form of the equation of a line is y equal mx plus b. Here, the slope is going to be m and the y-intercept will be b. Those are constants. Therefore, the function f of x equal mx plus b will have a straight line graph, and we call that a linear function. All right, so in this case, let's look at this first example. So here we're going to find out what the linear function is in this case. So let's say we want to find the graph of the linear function that passes through the points 2, 4, and 6, 8. So we got the points 2, 4, and 6, 8. We want to find out what that linear function is, and we want to graph it as well. Well, in this case, what we're going to do here is first plot those 2 ordered pairs on the coordinate plane, which are 2, 4, and 6, 8. So let's start with the points 2, 4. That means we go to the right 2 and up 4. That would be that point. And then the other point, 4, 6. To the right 4 and up 6. Now, it only takes 2 points to create a line. So I'm going to connect those 2 points here. And that will be the line right there. Okay. Now, I think in my math lab, you'll have to use that graphing tool to graph the linear function. So now let's find out what that linear function is. All right, this is going back to college algebra, where the first thing you need to do here is find the slope of the line passing through those 2 points. We're going to find the slope of the line passing through those 2 points, 2, 4, and 4, 6. So in this case here, the slope formula, and I'm going to say find the slope. The formula for finding the slope of a line through 2 points will be this. M is equal to y2 minus y1, all divided by x2 minus x1. Okay. Now, here x1 will be 2, y1 will be 4, and then x2 will be 4, y2 will be 6. So now in this case, y2 minus y1 will be 6 minus 4 divided by x2 minus x1, 4 minus 2. So 6 minus 4 will be 2. 4 minus 2 will also be 2. 2 divided by 2 is 1. So the slope of that line going through those 2 points will be 1. And now we use what they call point slope form to find the equation of that line going through those 2 points. And that's y minus y1 equaling to m times x minus x1. And in this case, I'm going to use, now I can use either one of these 2 points here. I'm going to use this first point, 2, 4. And if I use the point 2, 4, then that means that x1 will have to be 2, y1 will have to be 4. So here we're going to have y minus y1, which is 4. And that's equal to m, which is the slope that we just found, was 1, times x minus x1, which is 2. Now, 1 times x minus 2 will be x minus 2. So I'll just have y minus 4 is equal to x minus 2. And then to solve this equation for y, we add 4 on both sides to get y is equal to x plus 2. And since y and f of x mean the same thing, f of x would be just the equation x plus 2. So the linear function in this case will be f of x is equal to x plus 2. All right, let's look at the next example. Where it says here, a club plans to have a fundraiser for which $5 tickets will be sold. The cost of room rental and refreshments is $140. Find and graph the function P equals f of n that gives the profit from the fundraiser when n tickets are sold. Notice that f of 0 is equal to negative $140. That is, the cost of room rental and refreshments must be paid regardless of how many tickets are sold. How many tickets must be sold to break even? That means have a zero profit. Okay. Now, let's think about this for a moment. Of course, one of the ordered pairs is f of 0 is equal to negative 140. So one of the ordered pairs is 0, negative 140, which can be plotted on the coordinate plane. We stay at 0, but go down to 140 and draw that point. Okay, so if we sell no tickets, we still got to pay $140. There is a loss there because of the room rental and refreshments that have to be paid. Okay. Now, we can derive the equation just from this information that's given. All right, let's see here. $5 tickets are going to be sold to n number of individuals that attend. So that's 5 times the number of tickets, which is n. And then we have to subtract $140 off from the cost of refreshments and the rental. So it'll be minus 140. So here's what P is equal to. 5 times n minus 140. That would be the profit function. Okay. All right, now, let's do this here. Let's find out how many tickets must be sold to break even. That would give us a 0 profit. Okay, so now that P is equal to 5n minus 140. And we want a profit of 0 because that's the break-even point. So P has to be equal to 0. And that would be equal to 5n minus 140. Now to solve for n, we'll add 140 to both sides. So that means 140 is equal to 5n. Then divide both sides by 5. That will mean n is equal to 140 divided by 5 ends up being 28. So that means we need to sell 28 tickets to get a profit of 0 or to break even. Okay. Well, actually, that's another point on this graph. So the other point would be 28 and 0. So if I plot 28, 0 on the coordinate plane, you'll see that point would be on the x-axis. Okay, and this is enough points for me to draw the line of profit. Okay. So that's how we graph functions. All right, another type of function would be a piecewise function. Now, a function may have different definitions on different parts of its domain. And a good example of that would be income tax. That's usually levied in tax brackets that may have different rates or different tax rates. Functions that have different definitions on different parts of the domain are what we call piecewise functions. And if all the pieces are linear, then the function is piecewise linear. Now, on the next page are a few examples like this one. Here's a piecewise function, f of x is equal to, and we use 9 if x is equal to 4, or x squared minus 16 over x minus 4. That's used only for x not equal to 4. Okay. And we want to choose the graph that fits that piecewise function. Well, if you look at these, notice that they're all linear with a restriction. And the reason for that is this. We can simplify x squared minus 16 divided by x minus 4. Okay. Now that x squared minus 16, if you recall, is the difference of perfect squares, which means I can factor this into two binomials. That is, x squared breaks up as x and x. The 16, what number times itself gives you 16, has to be 4. And it's a difference of squares. That means that one must be plus, the other one has to be minus. And this is over x minus 4. And now we can simplify that by dividing out the x minus 4. And that would give us just simply x plus 4. And that restriction has to be where x is not equal to 4. That restriction still holds. Okay. Now the x plus 4 means that if we look at this, the y-axis is in increments of 2, and so is the x-axis is in increments of 2. That y-intercept is going to be 4, so it has to cross the y-axis at 0, 4, which is this right here. And at 4, if you were to graph this at x is equal to 4, you have to have what they call the hole in the graph. Okay. So it has to be B. Okay. And let me go into more detail with that by showing you this on paper. So in this case, these are in increments of 2 on the x and on the y. Okay. So if you were to graph this at 0, it would be at 4. So this is 2, 4, and that's on that point. But at 4, if you do 4 plus 4, that would be 8. 8's not included. So 2, 4, and then 8. At 8, you have to put the empty circle there for the fact that 4 is not included. That's the restriction. And I'm going to say at negative 4, that's going to be 0 as well. And notice the graph will not go through that empty circle. All right. And now at x equals 4, it will be 9, which is halfway between 8 and 10. Okay, so that's why it is into B. Okay, so that's pretty much how you graph a piecewise function. Okay. Now here's another example of a piecewise function that we're going to graph here. Let's say we got f of x is equal to, and we use 1 minus f, negative 1 minus x is if x is greater than, less than or equal to 2, and then negative 4 plus 2x is if x is greater than 2. So let's start off with f of x equal to negative 1 minus x. With the restriction that x is less than or equal to 2. And let's use a table of values here. We're going to select values that are less than or equal to 2, such as 2, 0, or 2, 1. Say 2, 1, and then 0, negative 1. And in this case, if x is 2, then negative 1 minus 2 would be negative 3. And then for x is 1, negative 1 minus 1 would be negative 2. For 0, -1 minus 0 is -1. And for -1, -1 minus itself is 0. So we're going to plot those on the coordinate plane. But -2, -3 will be to the left 2 and down 3. But -1, for 1 negative, I'm sorry, 2 -3. To the right 2 and down 3. 1 -2 to the right 1 and down -2. 0 -1, stay at 0 but go down 1. And then -1 0 to the left 1 and on the x-axis. So this graph will be going in this direction. We start at this point, go this way. Now for the other part, f of x equal -4 plus 2x if x is greater than 2. Okay, and the restriction there is that x is greater than 2. So that means we're going to start with 2, but at 2, we need to create what they call a hole in the graph, because we want to know where that hole in the graph will occur. And then values greater than 2 will be 3, 4, and 5. So for x equals 2, this will be 2 times 2, which is 4. 4 plus -4 is 0. So at the point 2, 0, you're going to have what they call the hole in the graph. And then for x equal 3, 2 times 3 is 6 plus -4 would be 2. Then for x equals 4, 2 times 4 is 8 plus -4 would be 4. Then for x is 5, 2 times 5 is 10. 10 plus -4 is 6. So now at 2, 0, we're going to have a hole in the graph at the point 2, 0. And then 3, 2 will be to the right 3 and up 2. 4, 4 will be to the right 4 and up 4. And then finally 5, 6 to the right 5 and up 6. So here's the other piece of that graph. Will look like this. So that would be the graph of this piecewise defined function, f of x equal to -1 minus x if x is less than or equal to 2, and -4 plus 2x if x is greater than 2. Okay, next we'll look at power functions and what their graphs looks like. Those are a special case of polynomials. They have the form f of x equal to x raised to the n, where n is a positive integer. And when n is an even integer, then the function values are going to be non-negative, and the graph will be passing through the origin, opening upward like these. Okay, so the one in black is going to be the one for y equal x squared. You can see that it's opening upward. And when x is negative, it's going to be positive. And the same will hold true for the y equal x to the 4th. You can see what that graph looks like. That's in red. The one in blue is y is equal to x raised to the 6th. And you see what that graph looks like. They all open upward because your exponent is an even integer. And for odd integers, the power function f of x equal x to the n has values that are positive when x is positive and negative when x is negative. Okay, and their graphs looks like this. The one in black will be for the equation y is equal to x cubed. And then for x to the y equal x to the 5th, that's in red. and the one that's in blue, y equal x to the 7. Okay, so when you raise a negative number to an odd power, it's going to be negative. And for an even number, a negative number to an even power will be positive. All right, next we'll look at root functions. Root functions are a special case. They have the form f of x equal to x to the 1/n power. N greater than 1 is a positive integer. So when n is even, which are square roots, fourth roots, fifth roots, square roots, fourth roots, sixth roots, and so forth, the domain and range consist of non-negative numbers, meaning we cannot take the square root of a negative number, nor can we take the fourth root of a negative number or the sixth root of a negative number. Those are undefined. Okay, so here's a graph of that. Okay, for y equal x to the 1/2, which is the same as the square root of x, and y equal x to the 1/4, which is the same as the fourth root of x, and y equal x to the 1/6. That's the same as the sixth root of x. Okay, it's only defined, the domain and the range only consists of non-negative numbers. So in this case here, we can say in interval notation, the domain is just going to be from 0 to infinity. Excuse me. From 0 to infinity for the domain. The range, same thing, 0 to infinity. Because we cannot take the fourth root of a negative number or the sixth root of a negative number or the square root of a negative number. Those are undefined. Now, by contrast, the odd root functions, which are cube roots, fifth roots, and so forth, are defined for all real values of x. And their range consists of all real numbers. And with these graphs, they pass through the origin and open upward for x less than 0 and downward for x greater than 0. And they flatten out as x increases in magnitude. Okay. So these are what the graphs looks like for y equal x to the 1/3, y equal x to the 1/5. Okay. And in these cases here, the domain is always going to be from negative infinity to infinity. The range is also negative infinity to infinity, since they're defined for all real values of x. Right on the next page. What I'm going to do here is omit this example. Okay, we'll omit this example here, dealing with a rational function. But do keep in mind, you may have rational functions where you have the highest exponent in the numerator and the denominator, like this. So now let's look at this example dealing with the function f of x is equal to x cubed minus 3x squared plus 6. And let's say we want to use a graphing utility to produce a graph of a given function and then give the domain of the function and then determine the peaks, valleys, and intercepts of that function. In this case, let's graph using the graphing utility. Okay, So the way I'm going to do this is press the y equal to button. I'm going to clear out any equations that have y1 in them. I want to make sure that my plots are off. If they're highlighted, you want to use your up arrow key and press enter. And then use your down arrow key to get back to y1. So under y1, I'm going to enter that equation x cubed minus 3x squared plus 6. So under y1, I'll type in the x, use xt theta n for the x. For the cube, I'm going to use the hat key, and then type in the number 3 for that exponent. So the x cube, use your right arrow key to get out of it, and then minus 3 xt theta for the n squared. Well, let me start over. X cube, and then minus 3 xt theta for the x. I need to press x squared for that exponent, and then plus 6. And I'm going to do, now notice down here, they give you the window to use. So to type in this window in our calculator, I'm going to press the window key at the very top. The -8, 8, and 2 represents the x and the range for that x. So from -8, that will be my x min. Now keep in mind the negative key is at the very bottom of your calculator. That's a dash with the parentheses. Okay, don't get that confused with the minus sign. So it'd be -8 for your x min. X max will be 8. Your x scale will be 2. And then press enter. The -16, 16, and 2, that's the window for the y. So your y min will be -16. Y max is 16. And your y scale will be 2. Then we press graph. Now you see what that graph looks like. And you want to pick the one that best fits the one that you got on the calculator. And by looking at it, I'm going to say this first answer choice would be the correct answer. So in this case, I'm selecting answer A. In case you want to pick the graph that best fits or looks like the one that you got on the calculator. All right, part B is to define the domain of the function. And then select the correct choice below, and if necessary, fill in the answer box to complete your choice. Okay. Well, let's think about this. This is a polynomial function, by the way. F of x equals x cubed minus 3x squared plus 6. It is a polynomial function, meaning that any x value that you assign to it, you will always get an f of x value for it. So that means the domain will be the set of all real numbers. So the domain there is the set of all real numbers. And then part C is to use the graphing utility to determine the peaks of the function. Okay. So going back to this, we're going to find out where the peak is. It's about right here. And we want that value to 2 decimal places. So what we're going to do is press second and trace for the calculate menu. Second, trace for the calculate menu. If we're finding a peak, we're finding a maximum. So we select menu item number 4 for maximum. I'm using the down arrow key to highlight that item for maximum and then press enter. Now for left bound, you're going to use your left arrow key to position that blinking cursor on the left-hand side of the highest value and then press enter. And then you're going to use your right arrow key to position that cursor on the right side of that peak and then press enter. And then after yes, go ahead and press enter. Now notice in this case, I got 1.9377 e to the negative 6. We call that a number that is written in scientific notation. So what scientific notation looks like is that. So let me move this out the way and write down what that scientific notation is. 1.9377 e to the negative 6. This means 1.9377 times 10 to the negative 6. We call that scientific notation. It's going to be a number that's between 1 and less than 10 multiplied by a power of 10. In this case, I want that as a regular number in standard form. That negative 6 tells me I need to move this decimal point 1, 2, 3, 4, 5 places. And 1, 2, 3, 4, 5, 6 places. So I need 1, 2, 3, 4, 5 zeros. So that decimal point will be in front of this 0. This will be in front of the 5 zeros and the 1. So that would be 0.000001937. And then we round to 2 decimal places. Well, obviously, the second digit in that behind the decimal point is a 0. To the right of that is 0. That's less than 5. So it's going to end up being 0.00. Now, keep in mind, it's not actually 0. It's just a number that is a little bit more than 0. So in this case, if the function has a peak at or near 0.00 to 2 decimal places. All right, and then next we're going to determine the values of the function. Well, let's look at where the value is at. It's down here. That's its lowest point that it will ever reach before it increases. So in this case, I'm going to do second and trace for the calculate menu. This time I'm going to select minimum, which is menu item number 3. So I'm going to go down there to minimum. Now for left bound, I'm going to put the cursor next to the, as close as I can to the lowest point, and then press enter. And then for right bound, I'm going to put the cursor to the right of the lowest point, and then press enter. And then after guess, we press enter. Well, here's your minimum right here, 2.0000004. Round that off to 2 decimal places, that would be 2.00. So the function has a value at or near x equal 2.00. And then next, we're going to find the intercepts of the function. Okay, to find the intercepts, we're going to find where does this point, what point is this graph cross the x-axis? So to do that, we're going to do second trace. Anytime you're finding the intercepts, you're actually finding the 0 of a function. So I'm going to use my down arrow key and select 0. That's the menu item. I'm finding out where does this graph cross the x-axis. And now for left bound, I'm going to put this blinking cursor on the lowest point on that graph. I'm going to put the blinking cursor below the x-intercept, and then press enter. Right down, put the cursor above the x-intercept. Press enter. After guess, go ahead and press enter. This will be to 2 decimal places. It says negative 1.19. To the right of it is a 5, so the 19 becomes 20. So it'll be negative 1.20. So the x-intercept is negative 1.20. And the y-intercept. Now, you can look on the calculator and go to second and graph. That will give you the table. And we're going to find out what y value will this graph be when x is equal to 0. So at x is equal to 0, your y is going to be 6. So the y-intercept in this case is 6. Okay. All right, next we'll look at using tables. Sometimes functions do not originate as formulas or graphs. They may start as numbers or data. Like, for example, let's say we want to take an experiment in which a marble is dropped into a cylinder filled with heavy oil and is allowed to fall freely. Here you're going to measure the total distance, which is d in centimeters, that the marble falls at those times from t is equal to 0 up to 7. And here's what the table looks like. And then the first step might be to plot those data points like we have here. And from that, by just looking at it, you might think that there is a function d equaling to f of t that gives the distance that the marble falls at all times of interest. Okay. Because the marble falls through the oil without abrupt changes, a smooth graph passing near the data points is reasonable, as you can see here. Now, later we'll talk about things like trying to find the best function that best fits the data, because right now that would be more difficult to do. Okay. Now, let's say we have this example. We want to consider t of n is equal to 1 squared plus 2 squared plus, and so on, all the way up to plus n squared, where n is a positive integer, which can be shown that t of n is equal to n times n plus 1 times 2n plus 1, all divided by 6. Let's say I want to make a table of t sub n for n is equal to, now in this case, this goes up to 7. Okay. Now, we'll just use that to come up with our values for t sub n. All right, so let's say t is equal to 1. All right, that means using this expression, that would mean 1 and then left parentheses, or better yet, let's do this. Let's go to y equal 2, and I'm going to clear this equation out. And I'm going to do this. The whole thing needs to be, everything in the numerator needs to be in parentheses. So I'm going to write this as t sub n is equal to, I'm going to put in the bracket n times n plus 1 times 2n plus 1. That whole thing will be divided by 6. When I enter this in, I'm going to use x instead of n. They all mean the same thing. So it'll be left parentheses for this bracket, and then n would be like x. So we type in the x t theta n for the x, and then left parentheses, x plus 1, close parentheses, and then open another set of parentheses for 2, then x plus 1, close parentheses. But then I have to close it again because I opened it right here from the beginning. And then that's going to be divided by 6. Okay. And then I'm going to do second and table to get my values here. So like for, let's look here. For n is equal to 1, that's what t is in. T of n is equal to 1. T of n is equal to 1. And then for n is 2, scroll down a bit, you can see at 2, it's going to be 5. And then at 3, T of n would be 14. And then at 4, T of n would be 30. And then at 5, T of n is 55. And then for 6, it'd be 91. And then at 7, it would be 140. So all I did there was just type in this equation in Y1 and came up with my values from the table. Now, in part B, you're going to choose the correct answer below. Well, we're told here, in this case, that n is going to be a positive integer. So our domain will have to be this one, the set of all n such that n is a positive integer. Okay. And then the least value of n for which T of n is greater than 1,000. Well, let's pull up this table that I came up with for that equation. Let's find out what value of n, or in this case, what value of x would give us a value for T sub n, T of n being greater than 1,000. Well, it's right here. Here we reach 1,015 when x is equal to 14. So at x equals 14, we're going to get a value greater than 1,000. So the least value of n is 14. Okay. Now let's look at transformations of functions and graphs. Now, this is one of those college algebra topics that was covered. And I have created a video for transformations of graphs on YouTube as well. There are several ways to transform a graph of a function to produce graphs of new functions. 4 transformations are common: shifts in the x and y directions and scalings in the x and y directions. These transformations are pretty much summarized in these figures here that you see here. Now, these two deal with graphs that are shifted vertically, as you see on the left, and horizontally, as you can see on the right. Okay, usually something shifted vertically, you're going to either go up whatever units or down whatever units. Like in this graph here, the one in black represents the graph of y equal f of x. And then you have y equal f of x plus 3. That means that the graph in black has been shifted up 3 places. And then for y equal f of x with a minus 2 on the outside, that means that the graph is shifted down 2 places. So these represent vertical shifts. The one on the right represents horizontal shifts. That means it's either shifted to the right or to the left. So for y equal f of x, which is the one in black, the blue one represents the graph shifted to the right. That's the y equal f of x minus 2. It's shifted to the right 2 places. Whereas for y equal f of, in parentheses, x plus 3, here the graph is shifted to the left 3 places. Okay. So with these horizontal shifts, these represent the opposite sign. If it's a minus, it's going to be a plus, so that means you shift to the right. If it's a plus, it's going to be minus, so that means you shift to the left. Okay, anything horizontal means you're going to shift in the opposite direction. All right, on the next page deals with scaling vertically. And also the one on the right deals with the reflection, as you can see with the negative sign. The one on the left in this case is the vertical scale by a factor of C. It's going to be wider if your constant is between 0 and 1, but it gets narrow when your constant is bigger than 1. So let's say the one in black is the y equal f of x. For y equal f of 1/3 x, you can see the one that's in blue, it's been wider, scaled vertically. So it's a vertical stretch. And this one that's in red is the vertical shrink. Okay, because it's shrunk vertically. Okay, now the one on the right is the reflection, because it has scaled vertically. This one has stretched vertically, but it has a reflection about the x-axis, meaning it's going to flip over and give you the mirror image. Now, the ones at the bottom represent this, scaled horizontally. That's a horizontal stretch or a horizontal shrink. Okay. As you can see here for the y equal f of x, which is in black, for y equal f of 1/3 x, it's been stretched horizontally. Okay. It's wider because the number in front of the x is between 0 and 1. Whereas for y equal f of 2x, the number in front of the x is going to get narrow. It's going to shrink in. Yeah, shrinks horizontally. Now, for this one on the right, there is a reflection. You still have your horizontal stretch and shrink, but the difference here is this is a reflection of the one on the left because of the negative sign that's in front of the constant. Okay. All right, now let's look at some examples here. Dealing with using shifts and scalings to graph the given functions. And then we can check by using the graphing utility. Okay. And then we want to identify the original function on which the shifts and scalings are performed, like in this one, f of x equal to x plus 5, quantity squared minus 6. Right, f of x equal to x plus 5, quantity squared minus 6. All right, notice here, I do see a plus 5 after the x. Here we have what they call a horizontal shift. In this case, it says plus 5. We do the opposite. Normally, we will move to the right, but it's next to the x is on the inside of the parentheses. We have to do the opposite, which is going to the left 5. And here the minus 6 tells me I have a vertical shift. Okay. Anything vertical means that the y is going to change, so that means we have to go down 6. And then we want the original function, what it was before these shifts came in. It would have to be something like x squared. So the original graph had to be f of x is equal to x squared. All right, so now let's plot this on our coordinate plane. So let's start with the f of x equal to x squared. Okay. At 0 is 0. At 1, 1 squared will be 1. At -1 squared will still be 1. And at 2, 2 squared will be 4. At -2 squared will be 4 as well. So we know this is symmetric about the y-axis. So here's 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. So the graph looks like this. Now, we're going to use the horizontal and the vertical shift here. So in this case, with this graph, we're going to be going to the left 5 and down 6 for each of these ordered pairs in f of x equal to x squared. Starting with, let's say, start with the origin here. We're going to go to the left 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6. For this point here on the left side, the y-axis, we're going to go to the left 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6. Then for this ordered pair, we're going to go to the left 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6. And then for this ordered pair up here, which is 2, 4, we go to the left 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6. And the other ordered pair on the right, that's 2, 4, we go to the left 1, 2, 3, 4, 5, and down 1, 2, 3, 4, 5, 6. So this is what the graph of f of x equal to x plus 5 quantity square would look like. That's the graph. And we can verify that by typing it into our graphing calculator. So in this case, I'm going to go to y equal to, clear this out. All right, so we're going to enter this function. So we'll do left parentheses, get your x plus 5, close parentheses, hit x squared to square it, minus 6. Now I'm going to do also in y2, x squared. Press the x, t theta for the x, and then square it. And then do zoom 6. Now this is the original graph, the original function f of x equal to x squared. But this is the one where we got f of parentheses x plus 5 quantity squared minus 6. Here's the graph where we shifted to the left 5 and down 6. Okay, let's look at another example. All right, let's say we want to use shifts and scalings to graph the given function, then check your work by using a graphing utility and identify the original function on which the shifts and scalings are performed. So like in this case, g of x is equal to negative 9/2 x squared. Well, obviously the original function had to start off as x squared. I mean, f of x equal to x squared. Now notice the negative 9/2 in front. That tells me that there is a shrink, which is going to be a horizontal shrink. There's also going to be something called a reflection because of the negative sign that's in front. Okay. So I pretty much already know what the graph is going to be for f of x equal to x squared. I can go ahead and plot those points on the coordinate plane from that last example. 0, 0, 1, 1, 2, 4, negative 1, 1, negative 2, 4. So that's the graph. Okay. And here's what I'm going to do. I'm going to use my graphing calculator to come up with the graph of g of x is equal to negative 9/2 x squared. So I'm going to go to y equal to, let me clear just the equation in y1. I'm going to leave the equation in y2 in. Now for negative 9/2, I'm going to do the negative key. I'm going to use my left parentheses for 9/2, 9 divided by 2, close parentheses, and then get my x by pressing xt theta. Now if I press zoom and then 6, correction, and y1. This should be x squared. I forgot to press the x squared button. You see, negative 9/2 x squared. I've got to press that. So let's do zoom 6 again. There's the original graph of f of x equal to x squared, but this is the g of x graph. That's equal to negative 9/2 x squared. All right, now let's look at the table for that. Second graph. Now keep in mind, I stored this in y1, so these are the values for g of x is equal to negative 9/2 x squared. Okay. All right. I'm going to pay close attention to the -1, 0, and -1 because those values are real small. So that way I can graph this on the coordinate plane. Like for 0, 0, that's okay. Now for -1, that's going to be -4.5. So that'll be to the left 1 and down 4 and about halfway between -4 and -5. And the same thing for 1 and -4.5, halfway between -4 and -5. And notice how skinny the graph looks like. There is that vertical shrink, vertical shrinking. So that's what that graph looks like. And finally, let's say we had g of x is equal to 3 times the quantity x plus 4 and that's squared. Let's find out what the original function is. Okay. Before the 3 and the x plus 4, it had to start off as x squared. So of course, f of x is equal to x squared. And I will go ahead and graph that in since I already know what the ordered pairs are. Okay, so here's the graph again of f of x equal to x squared. Now, for the 3 times the quantity x plus 4 squared, I'll put that in the calculator. So I'm going to go to y equal to, and again, I'm going to clear the equation in y1 so I can put this in. 3, left parentheses, hit your x plus 4, close parentheses, press x squared to square it. Then I'm going to do zoom 6. This is the original function, and this is the first equation. This is what g of x is. It's, of course, shifted to the left 4 places and is shrunk by a factor of 3. Now for the table, do second graph. In this case, let me use my up arrow key for something like -5, -4, and -3. That will help because that -4 is going to be 0. Here's -4, that's 0. At -3, that's 3. And at -5, that's also 3. So here's what that graph looks like. You can see that there is a horizontal shrink on that graph, and it's shifted to the left 4 places. All right. Also, I do have a list of all the transformations here that I picked up from a college algebra textbook that deals with things like the vertical shifts and horizontal shifts, the reflections about the X and the Y axis, also the vertical stretching or shrinking, and also horizontal stretching or shrinking. Okay. I do have other videos that I created that dealt with transformations of functions that I created for my college algebra classes, so you may want to refer to those in detail as well. Okay, so that does complete this video on section 1.2 dealing with representing functions. Feel free to email me if you have any questions about anything that's presented in this video, or if you have any questions about anything that's in the homework in my math lab. Okay, take care.